residential areas, understanding the primary voltages and transformer sizes is essential for electrical distribution. For single-phase systems, the common voltage is 120/240 volts. For three-phase systems, two common voltage configurations exist: 120/208 volts, known as YY, and 277/480 volts, known as delta delta. The phase configuration in residential developments typically involves single-phase circuits for smaller homes and apartments. Three-phase circuits are generally used for larger homes, multi-family dwellings, and commercial buildings due to their higher power capacity and efficiency. Transformer sizes vary depending on the electrical load demand of the customers they serve. For single-phase applications, common transformer sizes include 10 kVA, 15 kVA, and 25 kVA. For three-phase applications, typical transformer sizes are 15 kVA, 25 kVA, 50 kVA, 75 kVA, and 100 kVA. These sizes are selected to adequately handle the anticipated load while maintaining voltage stability. It is also important to understand the voltage drop calculations. Voltage drop is the reduction in voltage that occurs as electrical current flows through a conductor. Excessive voltage drop can cause lights to dim, motors to run inefficiently, and other electrical equipment to malfunction. The National Electrical Code, or NEC, provides guidelines for acceptable voltage drop limits. For branch circuits, the NEC recommends a maximum voltage drop of 3%. For feeders, the NEC recommends a maximum voltage drop of 5%. To calculate voltage drop, you can use the following formula: voltage drop equals current times resistance. The current is the amount of electrical current flowing through the conductor, measured in amps. The resistance is the opposition to the flow of electrical current, measured in ohms. The length of the conductor also affects voltage drop. Longer conductors have higher resistance, which leads to greater voltage drop. To minimize voltage drop, use conductors of adequate size. Larger conductors have lower resistance, which reduces voltage drop. Keep conductor lengths as short as possible. Shorter conductors have lower resistance, which reduces voltage drop. Use higher voltages. Higher voltages result in lower current for the same amount of power, which reduces voltage drop. When selecting transformer sizes, consider the load demand and anticipated growth. It is important to select a transformer that can handle the current load and provides sufficient capacity for future expansion. To determine the appropriate transformer size, you need to calculate the total load in kVA. Firstly, determine the total connected load in watts. This involves adding up the power consumption of all electrical devices and equipment that will be connected to the transformer. Secondly, apply a demand factor. The demand factor is the ratio of the maximum load demand to the total connected load. It accounts for the fact that not all devices will be operating simultaneously at their full rated power. Demand factors vary depending on the type of load and occupancy. Thirdly, convert watts to kVA. To convert watts to kVA, divide the total connected load in watts by 1000 to obtain kilowatts, or kW, and then divide the kW by the power factor to get kVA. Power factor is a measure of how effectively electrical power is being used. It ranges from 0 to 1, with 1 representing perfect efficiency. Most electrical loads have a power factor less than 1, which means that some of the electrical power is being wasted. Typically, a power factor of 0.8 is used for calculations. The formula is kVA equals kW divided by the power factor. Fourthly, apply a safety factor. It is always a good practice to apply a safety factor to the calculated transformer size. This allows for future load growth and unexpected surges in demand. A common safety factor is 25%, which means multiplying the calculated kVA by 1.25. Fifthly, select the standard transformer size. Transformer sizes are typically available in standard kVA ratings. Choose the next largest standard size that meets or exceeds the calculated kVA with the safety factor applied. For example, if the calculated kVA with a safety factor is 31 kVA, select a 37.5 kVA transformer, if that's a standard size, or a 50 kVA transformer. NEC Table 310.16 provides ampacity ratings for conductors based on their size, insulation type, and temperature rating. These ampacity ratings are essential for selecting the correct conductor size to safely carry the anticipated load current. For example, a 12 American wire gauge, or AUG, copper conductor with THHN insulation rated at 90 degrees Celsius may have an ampacity of 30 amps. To determine the appropriate conductor size, calculate the load current and apply any applicable dating factors. Dating factors account for conditions that can reduce the ampacity of a conductor, such as high ambient temperatures, multiple conductors in a raceway, or continuous loading. For example, if a conductor is installed in an ambient temperature higher than 30 degrees Celsius, the ampacity must be derated according to NEC Table 310.15. Similarly, if multiple conductors are bundled together in a raceway, their ampacity must be derated to account for the increased heat generated. Once the derated ampacity is determined, select a conductor size with an ampacity equal to or greater than the derated value. The NEC also provides guidelines for overcurrent protection devices, such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors and equipment from overloads and short circuits. NEC Table 240.4 provides the maximum allowable overcurrent protection for conductors based on their ampacity. For example, a 12 AWG copper conductor with an ampacity of 30 amps can be protected by a 20 amp circuit breaker. The overcurrent protection device should be sized to protect the conductor from overloads and short circuits, but it should not be so large that it allows excessive current to flow through the conductor. It's also crucial to verify the short circuit current rating of the transformer and electrical equipment. The short circuit current rating indicates the maximum fault current that the equipment can safely withstand without sustaining damage. This rating is essential for selecting appropriate overcurrent protection devices that can interrupt the fault current before it reaches a dangerous level. The available short circuit current at the transformer's secondary terminals must be determined through calculations or obtained from the utility company. Electrical panels and switchboards are designed to distribute electrical power to various branch circuits and equipment. These panels contain circuit breakers or fuses that protect the circuits from overloads and short circuits. Panel boards are typically located in easily accessible areas and are designed to be safe and reliable. The NEC provides requirements for the installation and wiring of panel boards, including grounding, bonding, and conductor termination. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and prevent electrical shock. Bonding ensures that all metal parts of the electrical system are electrically connected, which minimizes the risk of voltage differences and electrical shock. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods of bonding metal parts. Always consult with the local utility company for specific voltage and phase configurations used in a particular area.